You've probably heard of the thought experiment called Schrödinger's cat, and no, it's not about an actual cat. It's intended to illustrate an issue in quantum mechanics called the measurement problem. In quantum mechanics, events occur in a state of superposition. Literally, at the quantum level, multiple events can be occurring at the same time until they are finally observed, in which case the superposition resolves itself into a single event. It's a highly technical and heady problem that's rather elegantly explained with the thought experiment of Schrödinger's cat. But it may surprise you to find out that when Schrödinger introduced the idea, he was talking about something else entirely. It is history that deserves to be remembered.
It might seem surprising to a modern audience, but by 1900 the atomic theory of matter, that is, that all matter is made up of atoms, was not fully explained or even universally accepted. While the origins of the theory dated to the 18th or early 19th century, the exact nature of atoms was still not understood. Austrian physicist Ernst Mach, whose research on sound waves would lead to naming the speed of sound Mach, proclaimed after an 1897 lecture that "I don't believe atoms exist." Mach argued instead that atoms were just useful mental concepts for explaining observations, but not real. Mach was just one of a number of scientists who argued against the atomic theory in the 19th century. Despite some resistance, research on atoms continued to produce results. Right at the turn of the 20th century, English physicist J.J. Thomson's work on electrons showed that the atom was not the smallest form of matter at all, and in 1904 he proposed the first atomic model with subatomic constituents. His model, the plum pudding model, would soon prove incorrect, but the discovery that atoms themselves were made up of even tinier pieces would be critical to the formation of an entirely new field of physics. Problems with classical physics had begun appearing in the 19th century when traditional physics began failing to explain certain phenomena. There was, for instance, the Gibbs paradox, in which the expression for entropy appears to violate the second law of thermodynamics. Other issues also cropped up, such as with thermal radiation. When an object is heated, it becomes first red hot, and if it is heated further, will emit other colors, first yellow, white, and then blue, as it emits light at shorter wavelengths. A perfect emitter like this would, at cold temperatures, appear perfectly black, absorbing all light but emitting none. This ideal emitter was called a black body, and the radiation it emitted, black body radiation. And while they could explain experimental results at large wavelengths, at short wavelengths the theories strongly disagreed with experimental results. And, in fact, classical mechanics seemed to predict that at very short wavelengths, energy would be emitted at an infinite rate. This is called the ultraviolet catastrophe. Physicists developed a second theory that explained the results at short wavelengths, but which likewise failed to explain the results at longer wavelengths. The issue was not trivial, and scientists sought a single theory that explained all of the results. Max Planck was the first to explain all the results in 1900 with a new theory. Instead of imagining that energy could be emitted at any arbitrary amount, he proposed harmonic oscillators that were in equilibrium with the thermal radiation. Each of these oscillators, he said, emitted energy only at a single characteristic frequency. The energy emitted by any particular oscillator was therefore quantized. This idea would become known as the Planck relation, and the constant in the equation as Planck's constant. This was the first quantum theory in physics, and Planck was awarded the Nobel Prize in Physics in 1918 for the services rendered to the advancement of physics by his discovery of energy quanta. It's difficult to overstate how this understanding would transform physics. It was the foundation for the theories that would solve many of the issues in classical mechanics. In 1905, Albert Einstein applied the theory of quanta to a different issue. In the late 1890s, J.J. Thomson had discovered electrons. But in 1902, Hungarian physicist Philip Leonard was surprised that the energy of electrons ejected when light hits a metallic surface are not related to the intensity of the light, as classical mechanics predicted. Einstein suggested that for instantaneous transitions of energy, the energy in light might occur in a finite number of energy quanta. In his 1905 paper, On a Heuristic Viewpoint Considering the Emissions and Transformation of Light, Einstein wrote that when a light ray is spreading from a point, the energy is not distributed continuously over ever-increasing spaces, but consists of a finite number of energy quanta that are localized in points in space, move without dividing, and can be absorbing or generating as a whole. Albert Vossling, a German physicist turned scientific journalist, called this sentence the most revolutionary sentence written by a physicist in the 20th century. This work is what earned Einstein the Nobel Prize in Physics in 1921. The quantum theory of light was followed by the work of Danish theoretical physicist Niels Bohr, who used quantum theory to explain the emission spectrum of atoms. When gas is heated, it emits light at discrete frequencies. Bohr proposed a new model of the atom, which included quantized electron orbits. This created essentially our modern understanding of the atom, a dense nucleus surrounded by orbiting electrons that orbit at discrete orbits. When the electrons move from one orbit to another, they release photons at specific energies, creating emission spectrums. All these theories were really applied as corrections to classical mechanics, but not as yet as their own field. That changed as physicists continued to develop new explanations. In 1924, French theoretical physicist Louis de Broglie published the hypothesis that matter has wave properties, an idea that was proven experimentally. Two theories quickly followed: the development of matrix mechanics by German physicists Werner Heisenberg, Max Born, and Pascual Jordan, and wave mechanics developed by Austrian-born theoretical physicist Erwin Schrödinger. Schrödinger showed that the two mechanics were, in fact, equivalent. Schrödinger went on to apply the concepts to the hydrogen atom, describing four properties of an atom. Put together, they describe the electron's quantum state. Multiple physicists, such as Bohr and Heisenberg, attempted to explain the experimental results in what became known as the Copenhagen interpretation, after Bohr's institute in the Danish city where Heisenberg worked as an assistant. No actual definitive version of the interpretation exists, as the physicists held a variety of differing opinions. There were some characteristic ideas, however, such as that a system is completely described by a quantum state, and that atomic interactions are discontinuous. Others include the Born rule of Max Born, which says that the description of nature is essentially probabilistic, and Heisenberg's uncertainty principle, which states that we can't know both the position and speed of a particle with perfect accuracy simultaneously. More complex is quantum superposition, which posits that a quantum system can exist in multiple potential states until a measurement is made, when the wave function collapses into one of those states. The Copenhagen interpretation was far from universally agreed upon. Among the most notable critics was Albert Einstein himself. Einstein didn't have issues with the experimental results, but doubted the conclusions of some others like Bohr, and thought that quantum mechanics remained an incomplete theory. The disagreements are highly technical and have been repeatedly discussed among physicists. Much of it sprung from the idea that physicists like Bohr and Heisenberg believed their theory was complete. Born and Heisenberg wrote in 1928 that the theory was a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible to any modification. Einstein found that there were still significant unanswered or unsatisfactorily answered questions. One of the primary disagreements regarded the implications about the construction of reality. According to Heisenberg, physical reality was only defined at the moment of observation. Another issue stemmed from Heisenberg's uncertainty principle. In 1935, a paper was published under the authors Einstein, Boris Podolsky, and Nathan Rosen, which challenged the idea that the theory was complete. Entitled Can Quantum Mechanical Description of Physical Reality Be Considered Complete, and now generally known as the EPR paper, the paper attempts to construct a thought experiment paradox according to the rules of the Copenhagen interpretation. This thought experiment imagined two particles, A and B, which interact briefly and then move off in opposite directions. According to the uncertainty principle, it's not possible to measure both the position and momentum of particle B precisely, but you could measure the position of a particle A. According to the paper, finding the position of particle A meant that you could calculate the exact position of B, and finding the momentum of A, the momentum of B could be calculated. The argument was essentially that absent a direct observation, the momentum or the position of particle B could be measured, meaning that there was a reality to those things independent of their observation. This, the paper argued, meant that the wave function does not provide a complete description of the physical reality. Bohr objected and argued later that year that the paper's reasoning was faulty. For Einstein's part, in letters to Erwin Schrödinger, he said that the paper did not really represent his views and that it was mostly written by Podolsky. He said that the reality of particle B's momentum or position is a sausage to me, a German saying meaning that he couldn't care less. Instead, he focused on the issue of non-locality. It made no sense, he thought, that measuring particle A could lead to two states for particle B, no matter how far apart they were. Quantum states, as it stood, he thought, couldn't accurately reflect reality. The same year the EPR paper was published, Schrödinger wrote to Einstein to congratulate him for challenging the dogmatic quantum mechanics. The correspondence, which continued, was in essence a series of critiques of Bohr and his school. In August, Einstein asked Schrödinger to imagine if the small scale mechanics physicists talked about were enlarged. Suppose you had an unstable barrel of gunpowder that had an equal probability of exploding or not exploding in the next year. After a year, the mathematical equations in quantum mechanics would cease to make sense, as they would describe a sort of blend of not yet and already exploded systems. In reality, Einstein said, there is no such intermediary between exploded and not exploded. Schrödinger took that concept and imagined his own scenario, which he called a quite ridiculous case. Confined in a still chamber is a Geiger counter prepared with a tiny amount of uranium, so small that in the next hour it's just as probable to expect one atomic decay as none. An amplified relay provides that the first atomic decay shatters a small bottle of prussic acid. This, and cruelly, a cat is also trapped in the steel chamber. After an hour, he said, quantum mechanics would say the living and dead cat are smeared out in equal measure. Einstein liked the thought experiment. A wave function that contains a living as well as the dead cat just cannot be taken as a description of the real state of affairs. Einstein agreed, writing to Schrödinger, that nobody really doubts that the presence or absence of the cat is something independent of the act of observation. Einstein also had some philosophical disagreements regarding the Copenhagen interpretation's idea that quantum physics was essentially probabilistic and not deterministic. Famously, he wrote in 1926 that God does not play dice with the universe. He qualified this statement in a 1945 letter, writing that God tirelessly plays dice under laws which he himself has prescribed. Many have attempted in the years since his death to better understand his reservations and ideas about quantum mechanics. Schrödinger published his famous cat thought experiment in November 1935 in the German magazine Natural Sciences. He almost withdrew it when the Jewish editor of the magazine, Arnold Berliner, was fired due to policies of the Nazi government, but decided to publish it anyway at Berliner's request. The point was to highlight the incompleteness of the model, to critique the Copenhagen interpretation, but instead the thought experiment has become part of the foundation of quantum mechanics, much discussed in theoretical discussions. And to answer the obvious question, no, so far as we know, Erwin Schrödinger did not own a cat.
Bohr didn't respond directly to Schrödinger's paper, but the two continued to correspond, and in the end, the Copenhagen interpretation wasn't all that bothered by the observations of Einstein and Schrödinger. And actually, the concept that the cat can exist in two states at the same time is now a fundamental part of quantum mechanics, or at least at the quantum level. Scientists have continued to test quantum mechanics, and the Copenhagen interpretation is still the leading explanation for quantum mechanics. But the historical irony is that Schrödinger's cat is often used to illustrate the counterintuitive elements of quantum mechanics today. And the fact that he introduced the thought experiment not to explain quantum mechanics, but to challenge it, has largely been forgotten. I hope you enjoyed watching this episode of The History Guy, and if you did, please feel free to like and subscribe and share The History Guy with your friends. And if you also believe that history deserves to be remembered, then you can support The History Guy as a member on YouTube, a supporter on our community at Locals, or as a patron on Patreon. You can also check out our great merchandise shop or book a special message from The History Guy on Cameo.